Next up, we're going to be talking or hearing from Patrick McCorry and Segi Delgado about, so the topic is Towards an Accountable, Highly Available, and Fault-Tolerant Watching Service for Bitcoin's Lightning Network. Give them a warm welcome.
Thank you very much. All right, just before I actually get into this has probably been one of the few conferences where I've came to, and everyone's actually in the room and they're not in the hallway networking. So I want everyone to do a round of applause to say thank you for actually listening to these talks. You know, that actually shows that people are genuinely interested in this and not about meeting people. So what I want to talk about today is the PISA project, which is basically what we've been working on for the past 4 months. And the idea is that we're building an accountable, highly available, and fault-tolerant watching service. Now the question is, why do we need a watching service for? Why do we care about watchtowers? So all off-chain protocols rely on one big underlying assumption. And Udi pointed this out earlier, you know, having to watch out for disputes. But let's talk about it a bit concretely. We have Alice and Bob, and let's say they have a Lightning channel. Bob has sent Alice $1 million in the channel. You know, they're reckless. So Alice gets really excited. She goes offline, she goes to the Lambo dealer, and she's trying to convince the Lambo dealer that she has $1 million in this thing called Lightning, and she should be entitled to buy a Lambo. And while she's doing that, Bob is going to trigger a dispute. And then he's going to send evidence where he still has $1 million in the channel. Now, what happens is that this sets a fixed time period for Alice to respond and prove that she still has $1 million in the channel. But blocks are ticking away, and Alice hasn't responded yet. So the question is, will Alice wake up and save the day, or is Bob going to get away with it? In this case, she's happy, she responds, she convinces the blockchain she has $1 million in the channel, and she gets to keep her Lambo, you know, to the moon and all that. But she's a bit embarrassed, because she nearly lost her money, and was nearly bankrupt because of the Lambo. So 2 years ago, we thought about this problem, and we thought, you know, how can we help alleviate this new security requirement? You know, it's not reasonable that users have to remain online and synchronize with the network to watch out for these disputes. And this is basically the watchtower, although I call them leaning watchtowers because we're PISA. You know, it's a terrible joke. But the basic idea is that Alice will send a justice transaction to the watchtowers, and then the watchtowers will take this role on her behalf. Now, in the happy case, it's really straightforward. Alice and Bob do payments back and forth, although that's, you know, PowerPoint destroyed my slide. Alice then hires PISA. Alice goes offline. When Bob tries to cheat, the watchtower will just respond on Alice's behalf. So when Alice comes back online, she's happy, she still has her $1 million. Very straightforward. Now, how do people normally think about third-party watching networks? So this is typically based on private discussions I've had with people on how they think a watching network will evolve. So we have the user, Alice, on this watchtower network, you know, hopefully run by hobbyists. And what she's going to do is hire multiple watchtowers, and she'll send this out. Bam! Then she hires like 22 watchtowers. But can anyone see the obvious problem here? The problem is that, does she have to pay 22 watchtowers to watch this channel? If she does, you know, that's kind of expensive if you have to do that for every single state update. So the way we try to solve this problem typically is to have this on-chain bounty approach. The first watchtower to broadcast that justice transaction, to get it in the blockchain, will then claim the bounty. And that's basically what will happen here. And there'll be one winner who gets the bounty. You know, one winner, several losers. Now, if you're competing for a $5,000 bounty, that's probably a great approach. But if you're competing for a $5 bounty, it's not that great. And there's really 3 reasons why. The first reason is that in the current implementation for watchtowers, if Alice and Bob do 1,000 payments, the watchtower has to store 999 justice transactions. Basically, an encrypted justice transaction for every update in their channel. So there's order-end storage and order-end bandwidth updates. And that's a lot of load for a watchtower that doesn't get paid the $5. And actually, they have no idea, you know, if the dispute is solved, they don't even know they can delete watching. So that sucks a little bit. L2 will improve this with order 1 storage, but it doesn't solve the bandwidth issue as much. But that's not really the big problem. The big problem is who's going to be the winner. And the winner's going to be the miners. Because the miners can front-run the entire watching network. They produce the block, they stick in their justice transaction, and they broadcast it. They have an advantage over this entire network. So, just as a raise of hands, who would like to see the miners take on this watching network responsibility? Anyone here would like that? Raise your hand. No one. Why not? Exactly, why not? Sure, they have this extra responsibility. So I'm going to say, is that a good thing? I'm not going to say yes or no. I don't think they should. They should have a very simple rule of ordering blocks. But that's important. We can't compete with miners. And actually, in the Ethereum world, there is evidence of miners front-running users. I think like Ether, Delta, etc. So they will front-run if they can make money. But the worst case scenario is, what if you hire 22 watchtowers and nobody responds? You have no evidence, you hired any watchtowers, you have no recourse, there's nothing you can do. You just lost your money, and there's no outcome for that, and that sucks. So why do we have this design in mind? What are the fundamental goals we're trying to achieve of this? The first goal is trust minimization. We don't want to blindly trust a single watchtower to protect us. And the blindly part is really important. We care about high availability. If I hire 20 watchtowers, you will hope one watchtower will respond. And you want some fair reward. You don't want to hire a watchtower and they don't do anything. You want to make sure they actually do their job. So with Pisa, what we're really proposing is modifying that goal. We want to do trust minimization via accountability. So if the watchtower doesn't protect you, you can at least do something about it and prove their wrongdoing. It's sort of like Rusty's talk earlier about if you have a signed invoice, you can try to keep the second party honest. So in the original Pisa paper that we worked on 2 years ago, there was a smart contract with a large security deposit, like $10,000, $20,000, etc. The user has two pieces of evidence. One is a signed receipt that they actually hired the watchtower and the watchtower has accepted the job. The second one is on-chain evidence. If Pisa doesn't protect the customer, there's clearly evidence on the blockchain that Pisa didn't do its job. Now in Bitcoin, we can't, and obviously if Pisa doesn't do its job, the customer will use both pieces of evidence, submit that to the smart contract, and then Pisa will get sloshed and lose the security deposit. Now, for this to work in Bitcoin, we need a new opcode that can support SPV proofs and parsing the receipt. But we're not likely going to get that in anytime soon. So what we can do in Bitcoin today is reputational accountability. So if a watchtower doesn't protect me, at least I can tell everyone here about it. I can prove to you they didn't do their job, and hopefully you won't use their service, and then they lose business. So how does this work? And it's very, very straightforward. When Alice hires the watchtower, you send up your encrypted justice transaction and your payment. And the leaning watchtower will simply reply back with a signed receipt. Very straightforward. And the signed receipt at a high level contains the encrypted justice transaction, the transaction locator, which is used for finding the dispute on the blockchain, the appointment start and expiry time, and a signature from Pisa to say, I've accepted the job. Now let's say shit hits the fan. Bob triggers dispute, Pisa didn't do anything, Alice lost her money. How can we prove that Pisa didn't do his job? Well, first, given the signed receipt, anyone can verify the dispute happened, and that the dispute happened within the appointment time. The second one is that if anyone can then decrypt the justice transaction and they can verify that it was a valid justice transaction, it should have been broadcast and it could have get in the blockchain. And that's basically what we want to do at Pisa, is that in a simple signed receipt, they make watchtowers accountable. Now, one thing I want to finish on before Segi comes up is what is the role of a watching network? What do watchtowers do when you hire them? In my vision, they're a bit like insurance. They should take on financial liability for users who are offline. So if they don't protect you, then they have to refund you a pre-agreed amount. So you can actually get some money back if they don't protect you. One thing I want to highlight is what can a watchtower do and not do? A watchtower can protect you against crash failures if you go offline or if you crash. If you get hacked, your private key is stolen, or there's an insider threat, a watchtower cannot protect you there. It can only protect you against crash failures. There's a very simple rule in the network. Now, our Sergi's going to come up and talk about why Pisa is a boring, tedious, and very hard project. Good luck, Sergi. Cool, thank you.
All right, guys, thank you. So as Patty was saying, I'm going to be talking about the problems we have been facing with implementation so far, so why we think this is not that straightforward as it seems. So to start, who thinks this is a really interesting protocol and who would love to build watch hours? Raise your hand, please. A few of you, OK. We can talk later if you want. I mean, we are really interested in this. But mostly people are not that interested in this because there's like a lot of applications that actually are cool, and this is not a sexy protocol. You are like watching for dispute and so on. But on the flip side, this is something required for the Lightning Network to work properly because it helps to alleviate the always online assumption that Patty was referring to, right? So I want to highlight the problems we have been facing. We have created like 3 main categories of those. And normally, when you try to create a transaction within Bitcoin, if you have Bitcoin on the background, let's say, you may be facing a lot of like rejection issues from your node, depending on what you're trying to do, right? So imagine trying to do that blindfolded. You're receiving something that you don't know about, and then you decrypt it, and you try to send it. So the user can be set that up in multiple ways, either to like DOS you, or because they were not like they didn't know like how the fees were going to be, or so on and so forth. So basically, the 3 main categories we have here are non-deterministically verifiable things. Like, for example, when you're trying to submit the transaction to the network, it happens that the mempool is full. What can you do? I mean, you can see that the mempool is full, but you cannot prove that the mempool is full later on with your transaction only, right? You can rely on like third-party services to like take a snapshot and say, you know what, the mempool was full, but that's not something you can only check with your transaction. You also have deterministically verifiable things, like the transaction was invalid, the transaction was not standard, the fees were too low, the fees were too high, and so on and so forth. And this is tricky. This is like the broadest category, and it has both consensus and non-standard rules. And the problem with non-standard rules is that the transactions are actually valid, right? They are not standard, they're not going to be relayed, but the transactions are valid. So the user can always claim, mate, I sent you a valid transaction. You were not able to relay it. It's not my fault. So we need to like check how to do this properly if we want to be like accountable and reliable. And finally, we have topology-based attacks. So if you're trying to be there when someone else is not, someone may try to attack you because they want to DOS you so you cannot send the transactions on someone else's behalf. And here you can have Eclipse attacks, but you can also have other kinds of attacks, like more TX-probe-like, in the sense that imagine that you're connected to your neighborhood, and then someone knows that you are going to be sending a specific transaction. What they can do is send a double spending transaction to all your peers, and then when you try to send your transaction, bad luck is not going to get relayed. So, going a little bit more into detail, what are the problems here? First, for the fee, a watcher cannot bump the fee. A watcher is nothing but a relayer. And in order to do it, if, for example, we want to use child pay for parent, the watch hour will need a dedicated output. And that means that we are giving away some channel privacy, which is not ideal. If we are willing to give out channel privacy, then we can set up a completely easier watchhour protocol, but that's not what we want. Then we have revelation by fee, but that's something that the watchtower cannot do either because the watchtower cannot sign the transaction. We don't have any kind of keys. Then there's the ordered storage problem. That's the most well-known one. So basically, you have to store one job for every single payment, right? But there's more things in here. The things that you're receiving are encrypted blobs, and they can contain junk. And you're not going to be able to distinguish between junk and valid transactions until the dispute transaction is seen in the blockchain. Or even never, because if no one sends a transaction, you're going to need to store that until it times out. Then the amount of jobs you may get for a single payment is way higher than people used to think. So imagine that you have a 3-hop payment. If every single user in that route is getting the same watchhour to watch for that, that's going to be six jobs for him, right? So as Patty was referring, the bandwidth is also a problem. DOS attacks, I've already talked about it. we should also think that nodes crash, especially not only Bitcoin nodes, but like even your watchtower can crash. So if you rely that your watchtower is never going to crash, you're really lost. That's going to happen. And you should be able to know how to recover for it and what to do with the jobs you may have failed. And finally, handling reorgs and congestion. Congestion, I already talked about what happens if the mempool is full. But for reorgs, I mean, reorgs don't happen that often in Bitcoin, right? But who will bet $1 million in that a reorg is not going to happen? Who will bet like the reputation of the company in that that's not going to happen? You shouldn't if you're like working in this. You should have ways of like being able to recover from reorgs, and even though your jobs may have been finished, be able to like do it again if you need. So what's our approach for this? Our idea is to have a watching pool. The user will communicate directly with the coordinator of the pool, and will send the jobs to him, and then the coordinator of the pool will replicate all the jobs to the watching service, to the watching network, sorry. Then the idea is that if the coordinator crashes or it's deossed, the watchers can continue working. If one watcher crashes, the rest of the watchers hopefully will be able to finish the job. So you don't have like, I mean, you are able to still finish the jobs even though some of your watchers may crash. Right, so what's the current state of the project? As of right now, we're trying to work on a standard for watchtowers, so a way to like have watchtowers broadly adopted. We also have our closed source implementation, even though we want to open source it soon. For now, we have a REST API, but we are also working on a way to connect to the watchtower straight from the Lightning Network with the transport protocol of the Lightning Network. So I would like to do a really quick demo of the best case, as Patty was referring. So if we can switch to the video, we are like really tight in time, but I think we can do it. OK, so the idea here is that we have the dispute transaction and the justice transaction. The dispute is going to be the bridge transaction, and the justice is going to be what the watchtower is supposed to send to the network, right? We're going to be working in rectors because it's going to be like really, really quick. The idea is that we're creating the job. We put the dispute transaction in the transaction field, and the locator is going to be based on the dispute transaction ID. Right? So when we see the dispute transaction ID, we are able to respond. So what we have to do now is check at what time we want the watchtower to be hired. So we are checking the block count right now. It's 141. So basically, we should send the job at least in 142. We're going to make the job last at least 10 blocks, let's say. And now we can run the Pisa daemon, so the watchtower in one side, and the other side is going to try to send the appointment. So basically, we add an appointment to the watcher. Those are supposed to be different machines, like in completely different parts, right? So we create the appointment. The appointment is getting the information we got. It's encrypting the blob, and it's creating the locator, which is derived from the dispute transaction ID, and that has been sent to the server. The server has received the appointment. The locator is exactly the same one, and is waiting for disputes in the blockchain. Okay. So now we are basically going to double check that the justice transaction is not already in the blockchain, so we are not cheating here. Basically, let's do a get raw transaction and get transaction from our node, and we'll see that that's going to fail, both of them. Great. And after that, what we can do is send the dispute transaction. So we can go, get the dispute, send it to the network. Really, really tight. OK, boom, the transaction is sent. So if we go to the server side, we'll see that nothing happened yet, basically because the transaction hasn't been included in the block. So if the transaction is not in the blockchain, the watcher is not fired yet. What we're going to do now is basically create a block. Again, we are working in rectors to make it fast. So we have created one block. Now the server has received the block, and we can see like the list of transactions in there. We have some potential matches. Some of the matches actually match. So we have found one transaction that matched with one of the jobs we were assigned. Then we are able to decrypt the transaction and to push the transaction to the network. There it is. And there are no more appointments. We only send one appointment to the watcher. So what we're going to do now, fast forward, let's mine 10 blocks and see what happens. Yep. And then we can see like how a lot of blocks have been mined. And at the end, it says basically that the job has been completed when we go back. Blah, 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 blah. And there we go. Job completed. Appointment ended at block 152. Confirmation sent. OK? Great. Can we switch to the slides, please? Right, so that was my last slide. Basically, there are some reference there of like the vault we are working on and some technical documentation. So thank you all for watching, and I have no time for questions, so get me offline. Thank you.
Thanks very much.